Yes. So continuing with nomenclature of organic halides. Now we take up a few more examples. CH2Cl2. Common name is methylene chloride. Why methylene chloride? Because I told you last time, CH2 group is called methylene group, methylene chloride. If you have the feeling that methylene chloride should be one chlorine, then valency is not satisfied. And in order to satisfy valency, if you attach hydrogen, it becomes a CH3Cl. It is no more methylene. So it's understood that methylene will be CH2. Chloride is understood that it is dichloride. IUPAC name will be dichloromethane. CHCl3. Very simple compound. Common name is chloroform. IUPAC name is trichloromethane. Similarly, if this is CHBr3, common name will be bromoform. IUPAC will be tribromomethane. CCl4, common name carbon tetrachloride, or we can also call it tetrachloride. We can also call it perchloromethane. Perchloromethane, because all 4 hydrogen atoms of methane have been replaced by chlorine atoms. So 3 common names: carbon tetrachloride, perchloromethane, and third is tetrachloride. Now coming to the third common name, that is tetrachloride. In fact, tetrachloride, you may have the feeling any such compound which contains 4 chlorine atoms should be called tetrachloride. But if I say CCl4 is tetrachloride being used as the common name, then there is a reason behind it. See, like if it say Modi, then what strikes your mind? You probably will think of Prime Minister Modi. It's not that there are no other Modi in the world. There are so many Modis, but when we say Modi, you immediately, rather everyone immediately thinks of Prime Minister Narendra Modi. Similarly, because he is the most important amongst all Modis. Similarly, if I say tetrachloride, I should think of that tetrachloride which is most important. So remember, CCl4 is the most important tetrachloride. Therefore, tetrachloride is being used as the common name for CCl4. Right. IUPAC name is tetrachloromethane. Then CCl2F2. Common name is Freon 1,2. I hope you know chlorofluorocarbons are called freons. Now, what is the meaning of 1,2? That you will learn at the end of this chapter, because there's classification of freons. So this is freon. IUPAC name will be dichloro-difluoromethane. One word, alphabetical order, dichloro-difluoromethane. CClFBrI. No common name for this compound. IUPAC name will be just practice of alphabetical order. So IUPAC name will be bromochlorofluoroiodomethane. One word, bromochlorofluoroiodomethane. Then CF3CHClBr. If you remember, I told you this compound is halothane. Halothane. Now, in this case, this will be carbon 1, this will be carbon 2. IUPAC name will be 2-bromo, 2-chloro, 1,1,1-trifluoroethane. Right? We have to use locus rule, locant rule. So, and alphabetical order also. 2-bromo, 2-chloro, 1,1,1-trifluoroethane. Now coming to nomenclature of aromatic halides. One hydrogen of benzene is replaced by chlorine. Benzene minus 1 hydrogen is C6H5. This is called phenyl group. So the common name is phenyl chloride. IUPAC name is halobenzene, because IUPAC name is haloarenes, right? halobenzene. Now, common name of this compound. I hope you know about ortho, meta, para. First of all, let me tell you how do we use prefixes ortho, meta, para. You studied about these prefixes in 11th standard. Prefixes ortho, meta, and para are used only when there are two substituents on the benzene ring, neither less than 2 nor more than 2. Moreover, even if there are two substituents, ortho, meta, para is not used always, right? If used at all, then ortho prefix will be used when two substituents are at 1,2 position to each other on adjacent carbon atom. Meta prefix is used when they are at 1 and 3 positions. Like this one is, if this is carbon number 1, this will be called carbon number 3. If this is carbon number 1, this will be called carbon number 3. So this is meta. And prefix para is used when two substituents are at 1,4 position to each other. Now, coming to the common name, meta. See, if chlorine is not present, then common name of the compound is toluene. At meta position of toluene is chlorine attached. Therefore, common name is meta-toluene chloride. Meta-toluene chloride. IUPAC name 1-chloro-3-methyl benzene. 1-chloro-3-methyl benzene. Let's use this one. Common name para-dibromobenzene. IUPAC is 1,4-dibromobenzene, right? In common nomenclature, I'm using para. In IUPAC nomenclature, I'm using 1,4. So para-dibromobenzene common name, 1,4-dibromobenzene is IUPAC name. If you look at this structure, this appears to be a symmetrical structure because there are halogen atoms attached to alternate carbon atoms, alternate corners. Therefore, the common name is SYM symmetrical trichlorobenzene. Common name symmetrical trichlorobenzene. IUPAC name is 1,3,5-trichlorobenzene. Last three examples. This benzene ring with CH2 group is called benzyl group. Therefore, common name is benzyl chloride. Benzene with CH group is called benzyl group. Therefore, common name benzyl chloride. Although you can also write benzyl dichloride, but there's a system, we generally call it benzyl chloride, but benzyl dichloride is also correct as the common name. Benzene ring with C is called benzo group. Therefore, common name is benzo trichloride. Generally used trichloride, but if you write benzochloride, even then this is correct. Now, IUPAC name. This group, CH2Cl, attached to the benzene ring, this is called chloromethyl group. So IUPAC name will be chloromethyl benzene. This is dichloromethyl benzene, and this is trichloromethyl benzene. So with that, we finish nomenclature. Now coming to next topic, preparation of alkyl halides. We'll consider preparation of alkyl halides and aryl halides separately. Preparation of alkyl halides. See, alkyl halides can be prepared from three categories, three types of compounds. They can be prepared from alcohols. There will be three methods to convert alcohols into alkyl halides. They can be prepared from aliphatic hydrocarbons. Again, there will be three methods to convert aliphatic hydrocarbons into alkyl halides. And there are four special methods to prepare alkyl halides. So we'll study a total of 10 methods for the preparation of alkyl halides. So I'm starting preparation of alkyl halides from alcohols. And under this category, first method is by the reaction of alcohols with hydrogen halides. Right. So first method is to prepare alkyl halides from alcohols by reaction with hydrogen halides. Hydrogen halide means HX. One of the HX you're using in the lab also, HCl, but you never call it hydrogen chloride. You always call it hydrochloric acid. See, there's a difference between hydrogen chloride and hydrochloric acid. All hydrogen halides are gases. And when these gases are dissolved in water, the solution obtained is called hydrohalic acid. So HCl gas is hydrogen chloride. HCl solution in water is called hydrochloric acid. So in this case, in this method, we are reacting an alcohol with hydrogen halide to prepare alkyl halide. First of all, if I write X, X means halogen. Preparation of chloro, bromo, and iodo compounds will be studied together. If there's an exception, then I'll mention which halogen we are talking about. If I do not mention, X means maybe chlorine or bromine or iodine. Fluoro compounds are not studied along with the chloro, bromo, and iodo compounds. So their preparation and properties are altogether different. So alcohol reacted with HX gas gives alkyl halide and water. Now, the problem of this method is that water formed during the reaction reacts with alkyl halide slowly and therefore leads to a slow backward reaction. And if I want to prevent backward reaction, somehow I have to remove water from the reaction flask so that backward reaction does not take place. Now, how do we do that? Wait a minute. So how do we remove water? Now, for this, we'll take up preparation of chloro, bromo, and iodoalkanes separately. First, we take up preparation of chloroalkanes by this method. That is, halogen is chlorine. If I want to prepare primary or secondary chloroalkane, it means this alcohol should be a primary alcohol or secondary alcohol reacted with HCl gas. Reaction in this case is carried out in the presence of anhydrous zinc chloride. I get chloroalkane and water. I'll repeat. So for the preparation of chloroalkane, primary or secondary alcohol is reacted with HCl gas in the presence of anhydrous zinc chloride, leads to the formation of primary chloroalkane or secondary chloroalkane. Anhydrous zinc chloride absorbs water formed during the reaction and therefore prevents backward reaction. And this method is called Grove's method. So this method for the preparation of primary and secondary chloroalkanes is called Gross method. Water formed is absorbed by zinc chloride, and therefore backward reaction is prevented. Now coming to tertiary. If we want to prepare a tertiary chloroalkane, then tertiary alcohol is reacted with concentrated solution of HCl. HCl gas can be used, that is perfect. But even if you use concentrated solution of HCl which contains water and we want to get rid of water, even concentrated HCl can be used. There's no need to use anhydrous zinc chloride. Why? The reason is reactivity of tertiary alcohols is very high. Therefore, reaction will take place even in the absence of anhydrous zinc chloride, even in the presence of concentrated solution of HCl. Water formed will not be able to lead to backward reaction. Now, coming to preparation of bromo and iodoalkane. If I want to prepare bromo or iodoalkane from alcohol, then alcohol has to be reacted with HBr or HI, right? But the problem is HBr and HI are unstable compounds. Unstable means if they are kept for some time, they will undergo decomposition. It means to prepare bromo or iodoalkane from alcohol, HBr or HI which is used, that should be freshly prepared. And this freshly prepared should be so fresh that it is prepared in the same reaction flask in which it is to be used. I'll repeat, HBr and HI are unstable compounds. They are prepared in the same reaction flask in which they are to be used so that they do not get sufficient time to undergo decomposition. This type of preparation of any compound is called in situ preparation. In situ. So I can say HBr and HI are unstable. Therefore, they are prepared in situ by the reaction between sodium. Now, in this case, also we'll split bromo and iodo separately. To prepare HBr, we'll react NABr or KBr with concentrated sulfuric acid, which is taken in excess. See, let us say this is the reaction flask. I'm talking about preparation of bromoalkane. To prepare bromoalkane, I have to react alcohol with HBr. HBr is unstable, therefore I'll prepare HBr in situ. In the reaction flask, I'll take sodium bromide or potassium bromide. Number two, I'll take concentrated sulfuric acid in excess. Third, I'll take alcohol. First, these two will react together and lead to the formation of HBr. As soon as HBr is produced, it will attack alcohol and will give the final product. It means after HBr is formed, it doesn't get sufficient time to undergo decomposition, immediately attacks alcohol and leads to formation of final product, that is bromoalkane. So reactions will be NABr plus concentrated sulfuric acid, which is taken in excess, gives HBr plus NABr. NaHSO4. This will immediately attack alcohol. Now, how about this water, which leads to reverse reaction? If you remember, I told you concentrated sulfuric acid is used in excess. It means some sulfuric acid will be used to produce HBr according to first equation. Some extra sulfuric acid will be used, which will act as dehydrating agent. This leftover sulfuric acid will absorb water and prevent backward reaction. So that is in situ preparation of HBr. Now, to prepare compounds, iodoalkane, you might have the feeling we can carry out the same type of in situ preparation of HI. Ki or NaI with sulfuric acid will give HI. HI will react and lead to formation of iodoalkane. But there's a problem in this case. If we use sulfuric acid and sodium or potassium iodide, no doubt HI is formed. But as soon as HI is formed, before it attacks alcohol, before HI formed attacks alcohol, HI reacts with sulfuric acid and undergoes oxidation. HI plus sulfuric acid will give iodine, sulfur dioxide plus water. So as soon as HI is formed, this does not attack alcohol to give RI. Rather, HI reacts with sulfuric acid and leads to formation of iodine. It means we cannot use sulfuric acid. In place of sulfuric acid, concentrated phosphoric acid is used. So in this case, for in situ preparation of HI, what do we take in the flask? We take NaI or Ki plus concentrated phosphoric acid plus we use alcohol. First, these two will react together and lead to the formation of HI and NaH2PO4. This is sodium dihydrogen phosphate. This is also taken in excess. HI reacts with alcohol and give iodoalkane plus water. Again, how do we handle the problem of water? Extra phosphoric acid left is used here. Phosphoric acid is a very strong dehydrating agent, stronger than sulfuric acid. It will absorb water formed during the reaction, and therefore this will prevent backward reaction. So that is in situ preparation of HI for the preparation of iodoalkanes. Now, coming to the reactivity order of alcohols and reactivity order of HX in this method. See, to understand reactivity order of HX, that is HCl, HBr, and HI, and to understand reactivity order of primary, secondary, and tertiary alcohols in this method, we need to know mechanism of this reaction. See, this reaction takes place in 3 steps according to the mechanism. First step is, I'll speak, but I'll write in short, right? First method is protonation of alcohol. See, HX ionizes to give H plus and X minus ion. H plus ion is also called proton. H plus protonates alcohol. This leads to formation of this ion. Oxygen carries positive charge. Therefore, this ion is called oxonium ion. Oxonium ion. In second step, carbon-oxygen bond breaks. After this bond breaks, water is formed and carbonium ion is formed. Third step. Carbonium ion combines with halide ion and leads to the formation of final product, that is alkyl halide. Now, on the basis of this reaction mechanism, I'll explain reactivity order. First, I'll take up reactivity order of HX. See, in first step, HX bond is broken to generate H plus ions. If HX bond is weak, it will break easily. Formation of H plus ions will be easy and reaction will be fast. When will HX bond break easily? When it is weak. When is the bond weak? When bond length is more. Now, as we go down the group in halogen family, periodic table, as we go down the group, atomic size increases. Atomic size increases means HX bond length increases. HCl, HBr, HI. HCl bond shortest, HBr, and maximum bond length will be HI. It means HI bond length is maximum, bond is weakest, breaks easily. Therefore, reactivity of HI is maximum, followed by HBr, followed by HCl. So this will be HI more reactive than HBr, more reactive than HCl. This is the reactivity order of hydrogen halides, which is based on bond length and bond strength. Second is reactivity order of alcohols. You can see in second step, a carbonium ion is formed. That carbonium ion whose stability is maximum is most easily formed. And which carbonium ion is more stable or less stable, that is decided on the basis of hyperconjugation. If you remember, you studied about hyperconjugation in 11th standard. So on the basis of hyperconjugation, stability of carbonium ions is tertiary more than secondary, more than primary. Since tertiary carbonium ion is most stable, its formation will be easiest. And this is the reason reactivity of tertiary alcohol is maximum, followed by secondary, and primary alcohol will be least reactive. So reactivity order of alcohols will be tertiary maximum, followed by secondary, and then primary. With that, we finish this method of preparation.